Hello, good afternoon, everyone. Um, I'd like to continue with the pavement design. So, in this part, we're going to talk about the design traffic. So, in the design of pavement, so as we talk about it previously, um, the the traffic, the design traffic need to be to check with the allowable traffic loading. So the design traffic will contribute to the traffic loadings. So we need to find out how do we find the design traffic, and then later on it will need to be matched to the allowable traffic, allowable repetitions. Okay. So for example, just now I think previously we talked about for the mechanistic design. There are the pavement, there are many layers. So each one they respond differently. The asphalt differently, and then the cemented materials is upgraded differently. So the design traffic, it will be the same. We can design traffic initially. You know, the design traffic is in terms of the number of vehicles. Later on, we change to equivalent standard axle, and then we for the response, we need to change to the for the different layers, we need to change to the standard axle repetitions. So the standard, this one, the equivalent standard axle, it could be like 20 million ESA, but need to change to the for what is it equivalent to in the asphalt, what is it equivalent to in the cemented materials, what is it equivalent to the allowable this one, the standard axle repetition in subgrade. So that's we need to match. So the design for the rod to be for the pavement to be good without any failure, the design traffic need to be less than the allowable standard axle repetitions, or the SAR. Okay, so we need to look at the traffic, for how many years. You could design for 10 years, 20 years, 15 years. Okay, the role of traffic in pavement design, because it has been well established that light vehicles contribute very little to structural deterioration. Only heavy vehicles are considered in pavement design. Traditionally, the term commercial vehicle has been used to denote this vehicle. So the heavy vehicle is has much more contributions. Like I think I previously said that, let's say we have a small car, that is 1.2 tons, reasonable size car, 1.2 tons. So I have 4 wheels. So each wheel will exert about 300 kg on the road. Whereas for a truck with a gross weight of 20 tons, and then it has 1, 2, 3, 4, 5, 6 wheels. So each wheel will contribute about 3.2 tons for each wheel. So 3.2 tons compared to 300 kg. So it's about 10 times. So the truck, the loading, the traffic loading for each wheel of a truck or a heavy vehicle than the light vehicle. So comparatively, so the damage done by the heavy vehicle is much more. Okay, the damage caused to the pavement by the passing of a heavy vehicle depends not only on its gross weight, but also on how its weight is distributed to the pavement. In particular, it depends on the number of axle on the vehicle. The manner in which these axles are grouped together into axle groups. The loading applied to the pavement through each of these axle group, the axle group load. Okay, so we know that the heavy vehicles are heavy, but they also, you know, how these heavy vehicles, how is it work, what is it about, you know, the number of axle, the manner in which the axle are grouped together, and then all the load applied to each group through each of axle. So we have the number of axle on the vehicle. Okay, for example, let's say looks at this. This light vehicle is 2 axle. Okay, this one have 2 axle, 3 axle, 4 axle. This is 1, 2, 3 axle. Okay, look at heavier one. This one is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9 axle, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 15 axle. So so they have the number of axle is different, you know, from the rigid truck, which has probably about 2 axle, 3 axle, or 4 axle for the rigid truck, compared to the articulate truck, you know, they got about more than, sometimes it's 6 axle up to like 12 axles. The manner in which these axles are grouped together into axle groups. So there are few axle groups. So this one is just single axle with single tires, SAST, and then the single axle with dual tires, this one, and then tandem axle with single tire, tandem axle with single tire. So you got 2 axle grouped together, and then the tandem axle with dual tires. So that means it got 2 axle grouped together with both, they have dual tires. And then this one's tri-axle with dual tires, 3 axle, tri-axles, and then the quad axle with dual tires. Okay, so normally this is we have the like single axle, double axle, which called tandem axle. We have triple axle and triple axle, and then quad axle. So these are the how these axles are grouped together. The loading applied to the pavement to each of these axle group. So axle group load. So they have a certain loading applied to the axle group. So which we see later on. I think, where is that? Let me see. Just fast forward. So the loading group, like single axle 5.53 kilonewton, actually is 5.3 ton. Single axle with 12 tires 8 tons. Tandem axle with single tires 9 tons. Tandem axle with dual tires 13.5 tons. Tri-axle with dual tires 18.1 tons, and the quad axle with dual tires 22.1 tons. So these are the the loads applied through one group of axle, So each one of them, this one just 1 axle, and then 2 axle, 3 axle, 4 axle. In this group, like 4 axle. So the loading is 22.1 ton. Later on, we want to see that, you know, the single axle with the dual tires. This one actually is the that is standard. This actually is the equivalent standard axle. It's based on this single axle with dual tires. This later on it will be called the equivalent standard axle, ESA. Okay, so these are the various axle groups, and then these are some of these just the I think just the talk about the axle group, and then the vehicle types, the parameters. I think you can look at that, and then on the picture of those, what are the various class of vehicles based on the OSROD, class 1, 2, 3 until class 12. Okay, so these are various class of X. Normally the heavy vehicle will be starting from, I think, from the class 3. Class 3 is a heavy vehicles. You can see that heavy vehicles, medium. So so this one best, they have axle 2 or 3. So from class 3, 4, 5, class 1 and 2 is they are just considered as light vehicles. Heavy vehicles are 3, 4, 5. 3, 4, 5 onwards. Okay, so from this one onward, 3, 4, 5, 6 until the end 12. These are the heavy vehicles. But on the roads, we have to see the proportion of the axle group also. The proportion of heavy vehicles. What is the proportion? You know, for the rural environment, or the urban environment. Probably, you know, this one probably is more common, like smaller axle, 2 axle, 3 this one tandem axle. These are more common on the road rather than, you know, this road trend, you know, this big one. Probably they are quite they are the minority. There are these heavier classes, you know, the class 10, 11, 12, but there are not that many of such vehicles. So actually we need to find out what's the average axle for the heavy vehicles. What's the average axle? Later on we want to know about that, you know, that we will come to that later on. So there are so many axle group, but what is the average axle? You know, from we see here how many axle? You know, this one axle, you know, from 2 to 6, we have 6 more than 6 axle. This one actually is more than 6 axle. Okay, see, look at that. How many axle just now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 axle. So like this one's like this one, 1, 2, 3, 4, 5, 6, 7, 8, 9 axle. So later we need to find out what's the average axle for the heavy vehicles. The cumulative loading on a pavement over a period of time is in essence an account of every axle group traversing the pavement during this time period, together with its type and its load. The cumulative loading is specified by the cumulative loading. So that means that we talk about the not just a single day, but one, like I think it's for 1 year during this time period. The cumulative over a period of time in action in account. Okay, so the cumulative now is based on the cumulative number of axle group traversing the pavement during the period. Okay, so the proportion of each axle group in this the proportion of each axle group type in this total. So you have this one, the tandem axle. How many percent is that? If you got the triaxle, how many percentage is triaxle? Triaxle, you got single tire, you got dual tires. How many percentage are these groups? And then you got like this one, the quad tire, quad axle group. So how many percentage is the proportion? For each axle group type, the frequency distribution of the axle group types. Okay. overview of the procedure for determine the design traffic. So how going to determine the design traffic? The steps are select a design period. A design period, okay. Identify the most heavily trafficked lanes in the carriageway. Designate the design lane. Okay, you have many. Let's say you got dual carriageway. You have 3 lanes on one side for one direction, and then another 3 lanes on the other side from opposite directions. So for the 3 lanes, so you have to find the most traffic lane in the carriageway. So that we have to. So that means that which one is the heaviest load? Okay, the one with the heaviest loading. So we need to design for that most heavily trafficked lanes. Okay, so now because we are talking more about the heavy vehicle rather than the light vehicles. Okay, so most of the time the light vehicles, the faster vehicle, they will go at the fast lane. Let's say on the left-hand drive road, it will be the one near to the center. Okay, not the most of the heavy vehicle will on the left-hand side. Okay, estimate the average daily number of heavy vehicles in this design lane during the first year of the project life. So we estimate in the first year. Okay, first year of the project life. Later we can so we need to find out what is the number of heavy vehicle in the first year. Okay, first year of the design life. Later on we can based on that we based on the in that design line we can, because we have a growth, we have the growth of the heavy vehicles, because every year there might be let's say the growth of the heavy vehicles, maybe every year there will be growth of 5%. So next year will be like 5% more heavy vehicles, and then the next year will be another 5 increase again. So we just determine what is the cumulative heavy vehicle in the first year, okay, first year of the project, and then later on we have to multiply by the growth of the heavy vehicle. What's the percentage? Fourthly, estimate the heavy vehicle growth throughout the design period. Okay, so the growth of the heavy vehicles, how many percent? 5%, 6%, 7%, 8% during the design, throughout the design period. What's the design period? Okay, you do it for 5 years, or not at least like 10 years, 15 years, 20 years. Estimate the average number of axle group per heavy vehicle. So there are so many types of heavy vehicles with different axle group, ranging from like 2 axle to possibly like more than 10 axle. So what's the average number of axle group per heavy vehicle? If you've got so many heavy vehicles, so we just multiply by the average group, average axle. Colliers the above 3 estimate to calculate the cumulative heavy vehicle axle group over the design period. So with the we can find the design traffic to be based on the for the design period. What is the cumulative heavy axle group over the design period? So the loading will be based on the heavy vehicle. Okay, heavy vehicle. The calculate cumulative heavy vehicle axle group over the design period. Estimate the proportion of axle group types and the distribution of axle group loads. So this one estimate the proportion of axle group types. So like different, just now we have that we have like one axle, single axle, tandem axle, tri-axle, quad axle. So estimate what's the proportion, because in a vehicle, so the they got in a, like for example, in a heavy vehicle, like let's say you can six-wheeler, there will be one single axle group and then one tandem axle group. The tandem axle, there are two axles with dual tires for a truck, and then for a semi-trailer there could be they got single axle in front, and then the tandem axle, and then at the back there could be two tri-axle. Okay, so we try express the cumulative traffic loading in a form suitable for the specific pavement design procedure to be used. So the cumulative traffic loading, it will be, you know, the from the heavy vehicle loading, we can find the heavy vehicle loading, and then we can change it to the equivalent standard axle, and then we have to change it to the this one standard axle repetitions for each layers of the pavement, so that we can compare, you know, because we have a allowable standard axle repetitions for the wearing costs or asphalt, or for the cemented materials, and for the subgrade. So this one, the design traffic, you know, in terms of the ESA later on, they need to we need to change it to the for each of the layers. So they'll be under, like for example, the standard axle repetition for the asphalt, and then standard axle repetition for the cemented materials, and standard axle repetition for the subgrade. So that we know that, you know, the because we have the allowable, and then we've got the design traffic loading, so that we can compare whether, and from the computer we can work out that, you know, within the design period, let's say 15 years, to make sure that the design traffic loading to design traffic repetitions will not exceed the allowable repetitions. Okay, so we see the next. This is the flow chart for the procedure of determining the design traffic. So all this thing, like the step just now we talked about, the design period, design length, initial daily traffic vehicles, cumulative heavy vehicles for 1 year, and cumulative calculate the cumulative heavy vehicle axle group, cumulative heavy vehicle axle group, okay, HVAG. And from this we can have the establish a traffic lot distribution. Actually this one is the so this one is a heavy axle. This one, the distribution is like based on the ESA, heavy lot distribution. Okay, the HV. Oh, let me see. Just go and traffic lot distribution. So it will be actually the ESA. How many ESA per heavy axle group? This is a cumulative HVAG. HVAG. What is HVAG? Cumulative HVAG. Heavy vehicle axle group. Okay, the cumulative heavy. So this one determine the heavy. This NDT is the in cumulative heavy axle group. Okay, cumulative heavy vehicle axle group. This NDT, and this one will be the unit to be HVAG. Okay, HVAG. And for the estimation of traffic lot distribution, we have to find out, you know, for each HVAG, what is it the relationship with the ESA over HVAG. Okay, so because this one there's various ESA over HVAG. There are different value. For example, this one for the asphalt SAR, the okay, not this one. It will be this one. Okay, the based on the asphalt, you know, there are some ratio, because this one the SAR HVAG, just now HVAG, we change to actually you know, we can change to the SAR, you know, and then these are the ratio best. How many of this is the ratio from SAR based on asphalt to the standard equivalent standard axle. For the asphalt is 1.1. For rutting is deformation. For this one is for the subgrade is 1.6. For the cemented material fatigue, this ratio will become 12 actually. So this is actually the distribution of the traffic loading. Okay, so so from this we established the traffic loading, establish a traffic load distribution. So that is HVAG divided by ESA. So you could get some value, you know, for it could be different for the asphalt, and different for the cemented material, and different for the subgrade. So after that, then we go for the pavement. So we ignore the rigid pavement because we're not doing rigid pavement. So we do the flexible pavement. And actually from this traffic loading, you know, we could do the empirical design. So, you know, that one will be based on the ESA, empirical design, and calculate the ESA per axle group. So, you know, this one is where is that? I think it's in front. So the empirical so this one will be the based on this one. Okay, this one's for empirical design. Okay, the traffic loading, you know, so this one, the design traffic loading. If you got this traffic loading, then you can do the empirical this one, the design empirical methods to design for the thickness of traffic. This one match with the CBR, then you can do the traffic, find the thickness of the pavement. Okay, so for the mechanistic empirical design, so this one we have to calculate the ESA per axle group. So this one for this one, the empirical approach, empirical using the chart just now, the figure 8.4, you don't have to differentiate between the different layers. You don't have different, because that one you don't consider the asphalt as structural group. You only consider the pavement material and subgrade. Okay, so for that subgrade, for the pavement materials, they have certain CBR, and then for the subgrade they have CBR as well. But for mechanistic design, you have to find the cross. This one, the calculate the ASA per axial group and calculate the cumulative number of lot of each axial group type in axial lot. So this one, you have to find out the axial group types, you know, the ESA, but later on you have to be more specific because we need to target for each layer. So each layer will be slightly different, so the effect is different. And we talked about just now the we need to find out what is the standard because the allowable repetition, allowable standard axial repetition for the asphalt, for the cemented material, and for subgrade. So we need to find out what's the design standard axial repetition. Okay, so there's a factor to change the ESA to the SAR, standard axial repetition. It might be a bit confusing now, but there's a, you know, for there's standard axial repetition for the asphalt and standard axial repetition for the cemented material and standard axial repetition for the subgrade. So how we differentiate them is that we do the, like for asphalt, we put, you say SAR 5 for the we see 5 is, we know that is the for the allowable distribution. Okay, you know, for the once the design SAR 5 and then compare to the allowable SAR 5 for the asphalt. So the design one should not exceed the allowable. Similarly, for the cemented material, we have the design SAR. In this case is 12. Like 12, SAR 12. Okay, dimension for the cemented material, and for the for the subgrade is SAR 7. So we have to find out what is the design SAR, all this SAR 5, SAR 7, SAR 12, and then the allowable SAR 5, the allowable SAR 7, SAR 12. So those these are the just now the one, where did I put that? These are the conversion factor. You know, these are conversion. How you convert from the ESA to SAR 5, how you convert ESA to SAR 7, ESA to SAR 12. These are the conversion factor. So you know, when the design traffic, you will get the ESA. First, before that, actually we got the HVAG. HVAG will convert to ESA, but ESA later on will convert to this different SAR 5 or SAR 7, SAR 12. How do you convert that? These are the factor. So we can, you know, this one SAR 5 it will be equal to what is it equal to 1.1 times the ESA. SAR 7 will be 1.6 multiplied by the ESA. SAR 12 will be 12 multiplied by the ESA. Okay. Okay, so this one is the procedure to determine the design traffic. So just to summarize, you need to design for the you find out the HVAG, heavy vehicle axle group, and then later on you have to find out the ESA, the equivalent standard axle, and then from the equivalent standard axle you need to find out what is the design SAR 5, design SAR 7. SAR 5 is for the asphalt. The design SAR 7 is for the subgrade, and then the design SAR 12 is for cemented material. So, and then those are the design value, and then we have to look at the allowable SAR 5, allowable SAR 7, allowable SAR 12. Those value is based on the, you know, the previously we talked about that thing, you know, the based on this, you know, the allowable will be based on this. For the asphalt will be 5 here, and this one we later on will come out to be, we can the unit later on it will be, we have to based on the SAR 5, and those allowable SAR 5. This one will be allowable SAR 12 for the cemented material, and then this one we can get it. This one will be the allowable SAR 7 for the deformation, which is actually for the subgrade. Okay. Yep. So we got the determine the traffic, the design traffic. Procedure for determine the total vehicle axle group. Total vehicle axle group. So this one HVAG. So the first requirement of a pavement design is that it is adequate for the cumulative traffic loading anticipate in the design length over the design period. Okay, estimation of this loading firstly require the calculation of the cumulative number of heavy vehicle axle group over the design period. This design this, I think this is it designated NDT. So the calculation of cumulative HVAG is commonly broken down into the following region. So these are cumulative HVAG. Actually, this is the cumulative HVAG is NDT. Okay, this NDT is with this formula. So we first need to select the design period, identify the most heavily traffic lanes in the carriageway, designated the design lane. So you got 2 lanes. So which one is the most traffic lane? So we have to use that. You got 3 lanes. You have to find out which one is the among the 3, which one is the most heavily traffic lane. Estimate the average daily number of heavy vehicle in the design lane during the first year. Average daily. So for the first year of the project life, you find out, okay, the average daily number of heavy vehicles in this. Okay. So, and estimate the cumulative heavy vehicles over the design period, and estimate the cumulative heavy vehicles group over the design. Estimate the cumulative heavy vehicles over the design period. Okay, so that one we will find out what's the over the design period, and then later on we find out what's the cumulative heavy. After you find out the number of heavy vehicles, the cumulative, then you can find out the cumulative heavy vehicle axle group over the design period. Okay, so this is the equation. Okay, the NDT. NDT is the cumulative heavy vehicle axle group. So we have this 365 times AADT times DF times percentage of HV divided by 100 times LDF times CGF times NVAG. So what are these things? AADT. AADT actually is annual average daily traffic in vehicles per day in the first year. Annual average daily traffic in vehicles. So like one year you have 365 days. So what is the average for this road? What is the annual average daily traffic? Because the road may be every day they are not the same. So it could be like for this road it could be 1,000. Sometimes you have 1,000, sometimes 2,000, sometimes 5,000, sometimes 10,000. So what's the annual average daily traffic for this road? Maybe come out to be 6,500. So that's ADT is 6,500, and then for the 1 year you have to multiply by 365. DF, direction factor, is the proportion of the two-way ADT traveling in the direction of design lens. So the direction factor, you know, is if it's two-way rod, you know, that means that 0.5 direction factor. Okay. Yeah, so that, I think that is direction factor. So usually is we assume that half is going this direction, unless you got certain rod that's a direction factor. You know, certain rod has certain direction has more traffic. Normally we have probably we just we said that the one direction is 0.5, the other direction is 0.5. Percentage of HV, so average percentage of heavy vehicles on the road. So this one you probably they need to do some counting, you know, from the they can detect how many vehicles on the road, very heavy vehicle, the counting. Nowadays you got to put a tube, or you can just use the camera detection. So maybe 10%, 15%, 20% heavy vehicle. The heavy vehicle is based on like class 3, you know, class 3 truck, you know, with at least two axle. Land distribution factor. Distribution factor, proportion of heavy vehicles in design lane. So what is the proportion of heavy vehicles in design lanes? So for example, you know, land distribution like 3 lanes, 1.5, so 1. So this one is the, you know, this lane is the suggest limit for lanes. The distribution factor. So so these are how they distribute, you know, 2 lanes. So for two lanes, so distribution 1, this one's 0.1, and then this one 0.5. 1 and then 0.5, so 0.6. Okay, so I think we just, these are the value from the from this Osrod typical lens distribution factor. Okay. CGF, cumulative growth factor. This one will be based on later on. This one, cumulative growth factor. So it will be based on this formula here. R is the annual growth rate. What's the growth rate of the traffic? Okay, so all the traffic, because we this one, both the light and heavy vehicle. Okay, we want to find out what's the growth of the traffic in, you know, so, and the P is the design period, design. So this one based on, so from this one we can get CGF, cumulative growth rate. So the cumulative growth rate is this one. Okay, so, and then this one will take care of how many percentage is the heavy vehicle, percentage of heavy vehicle out of this one, the total this one, the cumulative growth rate, growth factor. Okay, and the NVAG is the average number of axle group per heavy vehicle. So you got so many type of so many axle groups. So like from the heavy vehicle, 2 axle to like more than 10 axle. So what's the average number of axle group? Is it 3 or 4 or 5 or 1 or 2 point something? Okay, so there's an average number of axle group. It may not be a round number. It could be some number with some decimal points. The design period adopted for the specific pavement type typically lies with the range indicated in these tables. So for flexible pavement, we design for 20 to 40 years. For rigid pavement, 30 to 40 years. Okay. identification of the design lanes. Okay, so this one, you have to identify. Common practice is to adopt the same pavement design for all lanes of the carriageway. Base this design on the traffic loading in the most heavily trafficked lane. This most heavily trafficked lane is termed the design lane. So even though the three, let's say you got 3 lanes, they are not equally trafficked, but we design them, you know, as for the pavement design, we make them the same design. So we don't prioritize, you know, we don't have a thicker pavement for the most heavily trafficked road, and these are thinner pavement for the least traffic road. So but we make it all the same. Okay. So we got all this thing, you know, the way in motion, that WIM. This one can find out provide lane specific heavy vehicle traffic load data across the carriageway. They can actually some of this thing we can find. They can find out which one is the most traffic lanes. If project specific information is available, then this table 7.3 provide guidance on the proportion of heavy vehicles traffic loading design in the traffic lane. So if you if you have this WIM, they can find out what is the proportion, where is the proportion of the traffic in the different lanes. If not, then we base on this one. Okay, let's say this is 2 lanes, 3 lanes, and these are proportion. 2 lanes, so 1 and 0.5, and 3 lanes is 0.95, 0.65, 0.3 for the rural. For urban is 2 lanes, 1 and 0.5. 3 lanes is 0.65, 0.65, 0.5. So these are so these are the distribution. The proportion as the proportion assigned to a specific lane is termed the land distribution factor for the lane. So this one, either you saw like this one, you choose 1. For this one, 3 lanes, you choose the design lane, like this LDF is 0.95, and for the urban 1, and then 0.65. Okay, so and then we put this LDF into this formula. There's a LDF here, so just put into the formula. Initial daily heavy vehicles in the design lane. To calculate the cumulative heavy vehicle axle group in the design lane, estimate is required of the average over the first year. So we need to find out what's the first year daily the average over the first year of the daily number of heavy vehicles in the design lane. So we want to find out in the first year of the roads, you know, let's say you have the data when you design the data, just the latest data that you obtain, then you can know how many in the design lane, what is the number of vehicles, average vehicle in daily vehicle. Okay, so maybe like 6,000 vehicles on the design lane. Okay, so later on, of course, because you got the percentage of heavy vehicles, so you can find out how many heavy vehicles. Okay, and then we have this the land distribution factor as well. So how much is that? Okay. Any of the following methods listed in descending order of accuracy may be used to estimate the initial daily number of heavy vehicles. So we could use these are methods that can be used. Weigh in motion, survey data either collected specifically for a project, or use of data obtained from vehicle classification counters, use of data obtained from single tube Excel counters or manual traffic counter. So actually there's some YouTube material on that, but I don't want to open it now. In New Zealand, the traffic counting program consists of a hierarchy of equipment that ranges from way in motion and vehicle classification collection via telemetry to simple portable tube traffic counters. So these are the methods to count the the daily traffic. So they can count the sometimes they put the tube across the line. Actually they count the like daily traffic. So that if they put it long enough, for 1 year, they can find out what is the average daily traffic based on that counting, based on the device they put on the cross rod. Either one of these, the way in motion or the second one or third one. Cumulative traffic volumes. So actually when they want to find out what's the traffic volume. So part of the task of estimating the part of the task of estimating the cumulative traffic in the design over the design period is to estimate the likely change in daily traffic loading during this period. So yeah, we will need to find out what's the change in daily traffic loading. Changes could occur both in the daily volume of traffic using the rod and also in the size of rod carried by the heavy vehicles. So the growth in traffic volume is considered in section. Okay, usually the rod we have certain, like we expect some and anticipate some growth on the traffic. We don't anticipate there's decrease in the traffic. Otherwise, we wouldn't do a new roads. Okay, if you anticipate there's no growth, there's a negative growth. Normally if you have construct a new road, you design a new road, you anticipate the traffic to grow yearly. Okay. If the project is realignment, construction, or an overlay, that's appropriate to base the estimation of growth in traffic volume on historical data for the existing road. Okay, so if you want to do okay, then the road is new, it's old, already been existent for 10 years. So you want to do some realignment, you want to reconstruction. So you want to do a new because some road is pass through a very hilly section, very winding section. You want to straighten the road, so you have a new alignment. So that one, the pavement design can be based on this historical data. Okay, so just based on the existing road, and then from that you can anticipate what's the yearly increase. If the project is greenfield project, that means totally new, then the estimation should be based on the growth experienced by similar roads in the vicinity, coupled with consideration of additional traffic to be generated by the ensuing land development in the corridor. So if it's a totally new project, you have to estimate based on the traffic of the road in the surrounding, the roads in the vicinity. So based on the surrounding, and you can sort of make a good estimate of the anticipate traffic on the road, okay, for the new roads, for new pavement. Daily volume of traffic, both light and heavy vehicles, will increase either for the entire design period or up to the stage where the traffic capacity of the road is reached. So the growth in traffic is geometric, and then this is a formula. You see cumulative growth factor. So it is a formula. So you based on the design period, is it 5 up to 14 years, and then what's the growth rate, 0 to 10 years, and then 3 you can find out what is the annual growth rate. It's 5%. You say you got 20 years, it's quite substantial. The growth rate is 20%, 22. It's quite a lot. Okay, so and then this CGF you put back into the here, so that will contribute for you to design, to find out what is the NDT, the cumulative cumulative HVAG. Estimate the axle group per heavy vehicle. So so you got many different type of heavy vehicles with different axle groups. So we need to estimate the average axle group per heavy vehicle. Okay, to estimate the cumulative heavy vehicles axle group over the design period, the average number axle group per heavy vehicle, NVAG. So this is the average number of axle group per heavy vehicle. Okay, so some ranging, the axle group ranging from 2 to 3, 4, 5, 6, 7 until maybe 10 plus. So what is it? What is the average? The method that may be used to estimate HVAG are weigh in motion or vehicle classification counter. Actually, they've got some methods to find the average axle group for a heavy vehicle. If you don't have, then we can based on this one. This is some sort of recorded data. So for the rural road, the average number of axle group per heavy vehicle is 2.8 axle. For the urban road, it's about 2.5. Okay, NVAG. So the axle group per heavy. So this one, the NVAG, is also inside this formula. Okay, so you multiply by this, the average number axle group per heavy vehicle. Then this one will contribute to us to find the cumulative heavy axle group later on. Estimation of traffic lot distribution. Okay, so we find from the cumulative HVAG. So this is the NDT. This is the NDT. This is the cumulative. We call the design traffic. But this one is the unit is in term of HVAG. Okay, the unit for this NDT is HVAG. So we want to find the traffic lot distribution. Okay. So we need to the traffic lot distribution for the project is required. In addition to the cumulative HVAG, the traffic lot distribution for the project is required to calculate design traffic loading. So we actually need to find the design traffic loading, and that means that we need to convert this HVAG to the design equivalent standard axle. So that means that the HVAG we need to change it to ESA, equivalent standard axle. So if it's if it's design standard axle design equivalent standard axle, then you just term it as DESA. Okay, basically the unit is the same, just that this one is for design. It actually is equivalent standard axle, and then if it's for the design purpose, then we just put a D in front. So the traffic lot distribution provides information necessary to evaluate the pavement damage caused by the HVAG. Okay, so this one the DESA, the design traffic. Okay, evaluate the pavement, specifically the proportion of all axle group that are a particular axle group types. For each axle group type, the proportion of axle applied at each lot magnitude. Okay, so we actually find out the average value, for the DESA, the equivalent standard axle. We got all sorts of traffic, but so we find the average axle. Okay. The calculation of ESA of damage due to the design traffic requires the estimation of average number of ESA per heavy axle group. So that means that how many we want to find out how many ESA per heavy vehicle axle group. So how many we need this conversion factor. Okay, how many ESA? We know that one ESA is equal to 8.2 tons. I think we have that. Where is that? So this is a 1 ESA. It's 8.2 tons. We want to find out what's the conversion factor, you know, from the HVAG. Okay. So the conversion factor for how, let's say the average number of ESA per heavy vehicle axle group. Okay, so we need to find out that later on. That means we want to change from NDT to which the unit which is HVAG. We want to change it to the ESA. Okay, so because there's different factor. Okay, so so actually there are so many different, you know, different type, you know, the like for example, you know, based on the different asphalt, based on the subgrade, based on the cemented material, there are different factors. So like 1.1, 1.6 or 12. So the conversion factor is, they're different. So we need to do it like for different layers of the pavement. We have a ESA, but need to yeah. Okay, I think I'm overshoot a bit. We want to find from the this one is HVAG to the ESA. Okay, because the heavy this one, so so that we can have same units. Because the heavy vehicle groups, heavy vehicle axle group, we can convert to the equivalent standard axle. Okay. From this one later on, we also need to sort of change it to the SAR, because the each of the layers have different response. We need to change to the design SAR 5, design SAR 7, design SAR 12, so that we can compare, because for the asphalt, for the cemented material, for the subgrade, the response is different. So we need to, from the DSA, we need to change to the various DSAR. Okay, so there are two things, there are two change from from the NDT, you know, the unit is HVAG. So you use this formula, then this unit that give you the units. This equation will give us the unit HVAG, and HVAG we can change to the SESA. We can change to ESA. Okay, so there's a conversion factor. Later on we have a look later on. Okay. So we're not going to see the WIM survey data either collected specifically for project or recently collected. Maybe used to estimate the traffic lot distribution, and later on for this project we need to get this factor later on. I think, where is that? Let me see. Okay. Okay. So we come to the next, the design traffic for the flexible pavement. The damage to the flexible pavement. The design traffic, okay, this one is described earlier, has to be converted into a form suitable for use in the flexible pavement design, NDT. Okay, so this one we need to convert to the form which can be used for the pavement design. There are two separate and distinct design procedures to follow. The empirical design procedure application. So this one is just this one, okay, the empirical approach. We just this one we just need a ESA. Okay, you just need an ESA, and then with the ESA you got the CBR. Then you can find the thickness of the pavement required. So that's the empirical design application. The second one is the mechanistic design application, applicable to the new flexible pavement contain one or more layers of bound material. So the bound materials will be the asphalt, and then so at least one. Okay, with the mechanistic design, normally we will a lot of time we design for the asphalt, which is a bound layer. Also we have a cemented material, so that's another bound layer materials. Okay, in the design of granular pavement with thin bituminous surfacing, only one type of damage is considered. So we could design with both the empirical or the mechanistic approach. But if you use the mechanistic approach to design for the granular pavement with thin bituminous surfacing, only one type of effort, which is the deterioration of the pavement, reflecting increased level of roughness and rutting. So this one actually is deformation of the subgrade. Okay, remember we said that for the pavement, for the deformations, we assume that there's no deformation in the pavement, no deformation in the base course or sub-base for this granular material pavement. So the deformation only happens at the subgrade. So yeah, so actually we only consider for the thin bituminous surfacing, we only consider this term only. We only consider this one, the deformation, permanent deformation. So we disregard for thin bituminous surfacing, we disregard the asphalt, we disregard the cemented material, only consider this one. Okay, if we use the mechanistic approach. So however, for pavement containing one or more bound layers up to 3 distinct types of the damage are considered. If you got asphalt, you got cemented material, and then the subgrade, then you have 3. So the defective damage to asphalt, rutting and loss of surface shape, this one is a subgrade, and the fatigue damage to the cemented material. So there are 3 types of damage, 3 types of pavement damage that we need to consider. Hence, overall there are 4 distinct types of damage which are considered in the design of flexible pavement. Okay, so 4 distinct: one for the empirical design, granular pavement, and up to 3 on the design of bound pavement. So one, if it's empirical design, whether you use it using the rational formula or CBR methods, or using the mechanistic design, there's only one damage, which is the subgrade. Okay, and if we use the bound pavements, then we have 3. We have to consider 3 damage, mostly 2 or 3. Okay, so if you use asphalt but no cemented materials, then it's 2 So it's the asphalt plus the subgrade. If you have a cemented material, there will be three damages, up to 3 damage. Design traffic loading is commonly described in terms of number of equivalent standard axle. However, it's not sufficient for the design of pavement containing one or more pavement layers. If you have only one damage. So if you have only one damage, that means you have thin bituminous surfacing, granular pavement. Then actually you can just use ESA. As we see that in the CBI method, we just need the ESA. In the mechanistic design, we also can use the ESA alone, because there's only one damage, so the ESA will be sufficient. They can check the design ESA and the allowable ESA. But if you have multiple layers, and then multiple layers can up to 3 type of damages. So for this reason, design traffic loading is expressed in terms of standard axle repetitions. So the ESA, if you have a lot of bound layers, let's say you have 2 bound layers and 1 subgrade, then we cannot use the ESA. We need to change to SAR, because each of the layers respond differently. So we have allowable SAR 5, allowable SAR 7, allowable SAR 12. So we need to, the design traffic, the ESA need to change to DSAR 5, DSAR 7, DSAR 12. Okay, I think almost finished. Just a minute, okay. Pavement damage in terms of standard axle repetition. Okay, in the flexible pavement design process, the first step is assessing the ability of pavement configuration to withstand the design traffic is to determine the extent of damage caused by the configuration by a reference axle group, termed the standard axle. Okay, for the pavement damage, so we need to have a standard axle group. The standard axle is a single axle with dual tires. Single axle with dual tires applying an axle load of 80 kN to the pavement. So this is the standard axle. 8.2 ton or 80, I don't know, here put 80 kilonewton. So it should be about, I think 8.2 ton actually is equivalent to 82 kilonewton. So yeah, I think probably about 80 or 82, you know, this is the standard axle. This is the equivalent, this standard axle is, so this one will be actually, we term as the, this is a standard axle. Okay, standard axle, the one that is we use. The candidate pavement is analyzed to determine the allowable number of standard axle repetition for each of the relevant damage type. Okay, so this one actually is one standard axle is equal to here put 80 kilonewton or 82 kilonewton, or in ton is 8.2 ton. So one ESA is called 8.2 tons. Okay, so but we need to determine the allowable, you know, the number of, we have this another unit is if we have the different bound layers, you have bound layer so that if you have 2 bound layers, then you have 3 type of damages. So you need to have 3 type of SAR, SAR 5, SAR 7, SAR 12 for each of the relevant damage types. These allowable SAR are compared with and need to equal or exceed the number of standard axle repetition that cause the same damage as the design traffic. So actually we need to the allowable, you know, we got the allowable damage, allowable standard axle repetition. This allowable, that means that you cannot exceed this allowable for the asphalt, for the cemented material, or for subgrade. Okay, if you acid it, it will cause damage. It will cause failure for the pavement. So we when design it, the design value of this DSAR, they should not exceed the SAR. Okay, the allowable. Okay, need to equal or exceed the. So in this case, that means that the allowable need to be more than the design. Okay. So this is a standard Excel repetition. So this one is the allowable need to be more than the design, so that the rod, there is not premature failure of the rods of the pavement. To calculate the SAR of damage, a procedure is required to calculate the damage association of each Excel group. Okay, lot on Excel this configuration that causes the same amount of damage. So these are the different type of Excel, and then these are the loading. Okay. So we have this sort of formula here. This is actually the conversion. So the SAR number of standard Excel repetition, okay, denoting this Excel group lot which cause the same damage as a standard Excel as the Excel group of is equivalent to is calculated as below. Standard Excel group. This one for the design. Okay, the design standard Excel repetition. Okay, this one. So this is the design one. So how we get this? Okay, so the design number of, so the SL is the standard lot for Excel group from table 7.6. So this one, these are value from here. Which causes the L, the top one L, is a lot magnitude of the Excel group type I. And the M is the lot damage, the exponent of the damage from table 7.7. This is table 7.7. So this is a SAM, you know, the if it's for the this is for the mechanistic design. So 5.712. This one actually is the same as the allowable, you know, that's just time previously we look at the for the asphalt, the exponent is actually 5, and then for the subgrade is 7, as for the cemented material is 12. Okay, lot damage factor for them. So we have this general form. Okay, denote the Excel group which cause the same damage as a standard Excel. Okay. Yeah, incidentally the 4 here, this one is just ESA. So the for the, if it's empirical, then you just have a ESA, the equivalent standard Excel, and then even in the mechanistic design, you can just keep the ESA. You don't need to change, because the DSA, you know, from heavy for design traffic from the heavy HVAG, heavy vehicle Excel group, you can convert to the ESA. But for the mechanistic design, for the bound layers, one or more bound layers, the ESA is not sufficient. You need to further convert them into the SAR5, SAR7, SAR12, and the exponent, you know, the exponent for this formula here, you know, is this one is this M here. M is so for the empirical, you know, if you use the mechanistic approach, the exponent is 4, but for the others, for the asphalt is 5, and for the subgrade 7, for the cemented material is 12. Okay, so this one, yeah, for the, if it's a thin surfacing, bituminous surfacing, you know, with granular, then you just for the with more than one damage, with more than one bound layers, then you have to use this one, 5712. Okay. Okay, the first step in calculating the SAR of damage due to design traffic is the calculation of design traffic loading in ESA from the cumulative number of heavy vehicle axle group. So this one we mentioned earlier. From the heavy vehicle axle group, you can convert to ESA. So the first step. This calculation requires the estimation of the average number of ASA per heavy vehicle group from the traffic lot distribution. Okay, this one ESA over HVAG, I think is actually not this one. Where is that? Section, okay, it's not here. Okay, there's some conversion factor. Okay, so we can see later. The traffic lot distribution may be based on this project specific WIM data we selected from, okay, presumptive DTA presented in appendix F. So I think I don't have the appendix D and F at the moment. The ESA over HVAG value for a range of selected site. Okay, there's you can get it from the, you know, from the on site. There's so that's the weigh in motion sites provided in the appendix D. So because it's quite a long table, I didn't put in. So I think it's you can see in the resource, because I put the pavement design. This one, the guide to pavement technology part 2. You can, if you're interested, you can look through. Okay, the presumptive TLD in appendix F is given in table 7.8 for the moderate to heavy traffic road. So these are the conversion. Okay, these are conversion. Okay, if it's granular, the conversion is just you know, the ESA divided by HVAG is 0.9 for rural. If it's for urban, it's 0.7. So for, if it's just one type of you know, if it's just thin bituminous surfacing and then granular pavement, then you just have convert from HVAG to ESA, 0.9 for rural and 0.7. But if you are using the bound layer, one or more bound layers, and then using a mechanistic approach, then actually you have to have different factors for different layers. So for you got the ESA, you actually from this one, and then you can, from the ESA, you convert to the SAR file, you know, ESA to SAR file for using these factors, 1.1. They are both the same, I think, for rural and urban. Okay. The design traffic calculated in terms of ESA of loading is converted to SAR of loading using the average, okay, value for each distress type. So these are conversion if you have one or more bound layers in the mechanistic design. These factors are determined from the TLD that is characterized actual or presumptive traffic data. The SAR divided by ESA for a range of selected WIM sites as provided in appendix D. Again, I don't have that. So, but these are the presumptive, this 7.8, so these are presumptive conversion factor. So these are the factor, because we cannot have just one single factor to convert, because there are different response for the asphalt, different response for the cemented materials, and then different response for the subgrade. Okay. I don't have that appendix H as well. If you're interested, you can look into the resource that are going to in the Moodle, talking about the this one, the appendix. I think that one, because there are so many tables from the WIMS, the way in motion side. The definition of design traffic loading and its calculation. So the design traffic loading for flexible pavement design is for each relevant damage type, the total number of standard axle repetition. So we have to find the SAR during the design period, which causes the same damage as a cumulative traffic. So so you see from first we have this one is the ESA. So the ESA, you get it from the this conversion factor. Okay, this conversion factor times the HVAG. Okay, so you get the DSA. Actually, this is in term of ESA. So average group, this conversion factor, average number of equivalent standard axle per heavy vehicles axle group. And then this one is from the formula, the long formula just now we look at. After that, you got the DSA from this with the unit of ESA, equivalent standard axle. Then you convert into this one, DSAR. So this is the design number of standard axle repetition to damage type. So depend on the M is the load damage exponent for the damage type. Damage type, you got the like 5 for the asphalt, 7 for the subgrade, and 12 for the cement materials. So like SAR 5 divided by ESA, SAR 7 divided by ESA, SAR 12 divided by ESA. So these are the here. So these are the conversion factor. We have this here. So the DSA is from previously. This one is in term of the the ESA. So DSA. So the design traffic in term of ESA, you can convert into the DSA RM. So that means that for this one will be 3 types for the bounded layer. For the bound layers, you got the DSAR 5 for the asphalt, DSAR 7 for subgrade, and DSAR 12 for the cemented material. So you got 3 types, 3 value. So yeah, so that's the design traffic, and then we'll compare this design traffic with the allowable traffic. Okay, I think we have talked enough about the design traffic, so I think I will stop here now.